Hello, today we shall see under classification of polymers, we shall see molecular characteristics, and under that subclassification we shall see the last subclassification, that is the molecular configuration and tacticity, and then we shall wind up this particular topic, which is molecular characteristics, the entire section, and summarize it. So, as we have seen, we are on the fourth classification, that is molecular characteristics. And under molecular characteristics, there are subclassifications. There are 5 subclassifications, out of which the first one, as we mentioned, that we shall see it as and when we look at each and every individual fiber and their structures. So the remaining 4, that is molecular weight, molecular shape, structure of the molecular chain, which we have already seen in the last lecture. Today we shall look at the last subclassification, that is molecular configuration and tacticity, how it affects the molecular characteristics. Uh, so we have seen the other 3, so we shall see the last one today. So what do we mean by molecular configuration? For polymers having more than one side atom or group of atoms bonded to the main chain, the regularity and symmetry of the side group arrangement can significantly influence the properties. So how this affects properties and how does it look like? Let us see. So we can, on the screen we can see 2 images here, and this is the R is the side group which is attached to the main carbon backbone chain, and in both the cases, as one we can see, this is attached on alternate carbon atoms, whereas this group which is there is attached on the adjacent carbon atoms. So consider the 2 configurations given above. R represents an atom or a side group, which is, maybe example can be either a chlorine atom or a CH3 group that is there. So in the first case, the side group is bound to the alternate carbon atoms, which is called as a head to tail configuration. Whereas in the second case, the side group is bound to the adjacent carbon atoms, which is called as a head to head configuration. So in most polymers, it is head to tail, that is the first type configuration that is seen due to the polar repulsion. So during the formation or polymerization, there will be repulsion between the groups, the side groups that are there, and because of that, normally one would find a head to tail configuration between the side groups. Because of the repulsion, one would very rarely find a head to head configuration, which is seen here. So, with this, we come to the next topic of discussion, that is isomerism. So, and what is isomerism and how it is found in polymers and what is it called? And because of this isomerism, how the properties of the polymer are affected, we shall see that shortly. So, hydrocarbon compounds with the same composition may have different atomic arrangements, a phenomenon termed isomerism. Simply, it means that although the atoms are the same in say 2 compounds, but just the arrangement of it in the molecule, one finds that different properties are imparted to these different arrangements. For example, there are 2 isomers for butane. Normal butane has a structure which is a linear kind, where all the carbon atoms are on a single backbone connected to each other, whereas the molecule of isobutane is represented as shown here. There are 4 carbon atoms in both these structures, but one is arranged in a linear fashion, whereas the other one can see the way it is arranged. So, some of the physical properties of the hydrocarbons will depend on the isomeric state. For example, the boiling temperature for normal butane is and isobutane is this. For a normal one, it is minus 0.5, and for the isobutane, the isomer of it, one finds that it has gone still below minus 0.5, that is minus 12.3 Celsius. So this has got a higher boiling point as compared to the isomer of this or isobutane. So we can see how the properties change. So similarly, one can see isomerism in polymers. So having the same atoms, one can have a different arrangement, and because of the arrangement, the properties of the polymers might change. So, isomerism is also found in polymer molecules, wherein different atomic configurations are possible for the same composition. Isomerism in polymers may be classified as stereoisomerism and geometric isomerism. So we shall see them one by one. Stereoisomerism is further subclassified as isotactic, syndiotactic, and atactic. So these are the three structures. Although on a two-dimensional plane, one does not find much difference between these three structures, but a three-dimensional structure would give a better idea, which is shown in the coming slides. Atoms are linked together here in the same order. It is the order is the same, that is head to tail, but they differ in their spatial arrangements. So although this looks different over here, like the groups are coming together sort of, but this is not the case. We shall see in the coming slides that they are all linked together in a head to tail fashion, but only the arrangement of this side groups in the space changes. So first one we will look at is the isotactic, where all the R groups, or rather the side groups, are situated on the same side of the chain. So one can see this is the carbon backbone that is there, which is a linear backbone, and one can see this green balls that are shown here. They are connected in the same on the same side of the main chain. So this kind of a arrangement is called as isotactic. So we come to the next one, that is syndiotactic, where the R groups alternate sides of the chain. So although the backbone chain of carbon atoms is the same, here one can see that this R group or the side group is coming on in the space it is arranged around, rather than in the earlier case where it was placed where this hydrogen atom is placed. But in this syndiotactic, the spatial arrangement has changed. This R group has come on this side, and it alternates every time here, and on alternate sides it is there. So this type of a structure or arrangement is called as a syndiotactic. We come to the atactic, where it is randomly positioned. The R groups are randomly positioned. That means they can be anywhere. These three you can see on one side, then R over here, two R's over here, and then again it comes on the same side, and so on. So they can be positioned in a random way along the main chain length, which is called as an atactic. So tacticity of a polymer. Tacticity means it is the spatial, or in the space how they are arranged, spatial disposition of the substituents attached to the asymmetric carbon atoms in the chain. It influences the packing of the molecular chains and therefore the crystallinity. So because of this tacticity that is there, the spatial arrangement, simply by changing the arrangement, the packing of the molecular chains get affected, and therefore the crystallinity of the final polymer is affected, and because of which other we shall see later, because of crystallinity many other mechanical properties, thermal properties change because of this. So they are all interconnected. So isotactic, since it is identical spatial disposition, syndiotactic is alternating configuration, and atactic is completely random and may be considered as a combination of isotactic and syndiotactic. So isotactics, one will find that since they are all arranged in the same on the same side of the group, side groups are arranged on the same side of the backbone. They are usually highly crystalline, whereas syndiotactics show a good tendency to crystallize as compared to atactic. So the crystallinity order is the highest in isotactic, then the syndiotactics, and atactics are less crystalline polymers. So conversion from one stereoisomerism to another, example isotactic to syndiotactic, it might seem that we have to just change the spatial arrangement, but it is not possible by a simple rotation about the single chain bonds. That is what we are trying to say. The bonds must be first severed. That means the bonds need to be break, and then afterwards appropriate rotation needs to be done, and they are then reformed. So it is not easy to change from one isomerism or one isomer to the other. In reality, a specific polymer does not exhibit just one of these configurations. The predominant form depends on the method of synthesis. So, in any specific given polymer, one will find that all of these configurations might be present, but the predominant one, the one which is majorly found in that particular polymer, that would be the one can say tacticity of that particular polymer, and this is decided during, or it is decided by the method of synthesis. So during synthesis, if certain things are followed, then one can obtain the polymer in the isotactic form, or once you change the during the synthesis, if some certain conditions are changed, one can get the atactic form. So method of synthesis decides which tacticity will be more predominant in a given polymer. So now we look at the next type of isomerism, that is geometric isomerism. Other important chain configurations of geometric isomers are possible within repeat units having a double bond between chain carbon atoms. So if in case the main backbone chain has got double bonds in itself, then again there can be isomers of this type of polymer, and let us see what they are. In this case, the side groups may be situated on one side of the chain or on opposite side. Consider the isoprene repeat unit having the structure in which the CH3 group and the H atoms are positioned on the same side of the double bond. So this is an isoprene repeat unit where we have a double bond between two carbon atoms, and one can see the CH3 group is arranged here along with the H atom, whereas on the other side it is CH2 groups, both are there on the same side, whereas CH3 and H are on this side. So this particular where it is there are positioned on the same side of double bond. This is termed as a cis structure, and the resulting polymer is cis polyisoprene, which is a natural rubber. So we come to the next structure, that is the trans. So in the trans structure, CH3 and H are on the opposite sides of the double bond. So if you look at the structure now, the CH3 and H are on the opposite sides as of this double bond, as one can see. So trans polyisoprene, sometimes called gutta percha, has properties that are distinctly different from the natural rubber. The earlier one, the cis type we saw, it is natural rubber, whereas this gutta percha is a completely different polymer, which has got different properties when compared to natural rubber. And this is only because of the configurational alteration that we see, that is the CH3 group and the H atom are on the opposite sides of the double bond. So if we know what is this gutta percha, we'll be able to understand better. So gutta percha is a material used to fill a tooth after root canal procedure. It is a plastic substance from a Malaysian tree called as a percha tree, and is used as a permanent filling in root canals, and this polymer is thermoplastic in nature, and it's a natural polymer that is found. So conversion of trans to cis or vice versa is not possible by a simple chain bond rotation. Again here it seems fairly simple that one can just rotate the chain and get the two isomers, cis to trans, and it can be converted from one to other, but it is not so, because the chain, that double bond is there, this is extremely rigid, and the conversion from trans to cis or vice versa is not as simple as it looks. So now we come to the summary of the entire section on molecular characteristics. We had seen 4 subclassifications, and now we shall see the summary and try to revise and recollect that we have learned in the past few lectures. So summarizing the preceding sections, polymer molecules may be characterized in terms of their shape, their size, and the structure. Molecular size is specified in terms of molecular weight or degree of polymerization. Molecular shape relates to the degree of chain twisting, coiling, and bending. Molecular structure depends on the manner in which structural units are joined together, whether it is linear, branched, cross-linked, and network structures are all possible. in addition to several isomeric configurations, which is isotactic, syntactic, atactic, cis, and trans. So we can classify this and put it in the form of a chart like this. So molecular characteristics, they would be classified as one is, first one is the chemistry of the repeat unit composition, which we said that we'll see later when we see the fibers. So we have seen these size, that is the molecular weight, the shape, and the structure. So molecular size means molecular weight and the dp. The shape means the whether the molecule, the chains are twisting or are entangled. Even these will affect the molecular characteristics or the polymer properties. Then the third one was structure. Under structure, we saw the various structures that are linear, branch, cross-linked, and network. Then we also saw the isomeric states that polymer can exist in. So stereo isomers and geometric isomers. Under stereo, we saw isotactic, syntactic, and atactic, whereas under geometric, we saw cis and trans. So one thing to note here that some of the structural elements are not mutually exclusive. So although it looks like a classification over here, the properties may not be mutually exclusive. For example, it may be necessary to specify molecular structure in terms of more than one. For example, a linear polymer may also be isotactic. So if it is linear polymer which is there, now we all know what is a linear polymer. It may be isotactic in nature. So it is not mutually exclusive that if it is linear, it will not be isotactic and so on. So the structural elements, as we can say, they are not mutually exclusive. Both of them can coexist in the same polymer. So with this, we have seen the classification of the characteristics of polymer. That is, we have come to the fourth point, that is molecular characteristics, and we have covered all the types under that and subclassifications under molecular characteristics. So with this, we come to the end of this lecture. Thank you.